Hello class, in this video we'll learn how to interpret an energy profile diagram. To do this successfully, I'm going to need to introduce a few concepts first. Firstly, I'll discuss what is collision theory. Collision theory states that for any chemical reactions to occur, there needs to be successful collisions between reactant particles. Successful collisions are characterized as collisions where the reactants are colliding with sufficient energy so that the bonds are broken within the reactants. This is illustrated here in the following animation, where you can see that fast collisions result in a chemical reaction, whereas no reactions occur with a slow collision. Another requirement is that reactants need to collide with the correct orientation, meaning they need to be facing a certain direction for the reaction to occur as well. We define the minimum amount of energy that reactant particles must possess to commence the chemical reaction as the activation energy. You can think of the activation energy as an energy barrier or a threshold that must be overcome for the reaction to proceed. If a reaction has a high activation energy, it is harder to initiate the chemical reaction. However, if the activation energy was low, it is more easier and likely for a chemical reaction to occur because reactant particles would be able to meet the energy requirement. In the diagram below, we can explain why the following reaction is successful by referring to the principles of collision theory. This is because A, the reactants are colliding with the correct orientation, and B, the kinetic energy of the reactants in which they collide is greater than the activation energy. On the other hand, the second collision does not result in a chemical reaction because A, the orientation is incorrect when the particles are colliding with one another, but also another reason could be that the energy of the collision is lower than the activation energy, hence no products are formed. We can illustrate the energy changes of an exothermic and endothermic reaction using a diagram commonly referred to as the energy profile diagram. The energy profile diagram for any chemical reaction will have the following general shape and is often labeled outlining both the change in enthalpy as well as the activation energy of the reaction. I would like to mention that the activation energy barrier is present for both the exothermic and endothermic reaction, but you will soon see that the activation energy for the exothermic reaction is generally lower compared to an endothermic reaction. If we were to calculate the change of enthalpy for the diagram on the left, this will result in a negative value, which indicates that the energy profile diagram on the left is for an exothermic reaction. In contrast, the delta H value for the diagram on the right is positive, hence the energy profile diagram for all endothermic reactions will have a similar shape. The activation energy, represented by the letters EA, is depicted by the height of the heel on the diagram. The larger the activation energy, the height of the heel displayed on the diagram will also increase in size. I would like to emphasize that the activation energy will always take on a positive value because it is the energy required to break the bonds within the reactants. Let's quickly stop for a moment and check for your understanding. Pause this video now and identify which of the following labels corresponds to the activation energy. The correct answer to this question is going to be A, as it's always measured from the reactants to the tallest peak. Let's now go through an example of how to interpret the magnitude of the activation energy and enthalpy from the energy profile diagram. Since we know that the activation energy is measured from the reactants to the tallest peak, we will find the difference between 70 and 5. As a result, this will give us an answer of positive 65 kilojoules per mole. The change in enthalpy can be found by subtracting the enthalpy of the products with the enthalpy of the reactants. If we subtract 50 and 5, we will get an answer of positive 45 kilojoules per mole. The positive delta H value and the general shape of the energy profile tells us that this reaction is going to be endothermic. I would now like you to have a go. Pause this video now and see if you can find the value of the activation energy and delta H. In this question, the activation energy can be found by subtracting 200 with 140, giving us an answer of positive 60 kilojoules per mole. The change in enthalpy can be found by subtracting 100 with 140, which equals to negative 40 kilojoules per mole. This value suggests that the reaction is exothermic. In the next section of this video, I would like to talk about reversible reactions, which is a topic that also overlaps with chapter 8. In some chemical reactions, the reactions occur in one direction where the reactants are converted into products. However, in a reversible reaction, the products can also be converted back into reactants. To represent a reversible chemical reaction, double arrows are used in a chemical equation. If we know that the reaction is exothermic in one direction, this means that it will be endothermic in the opposite direction and vice versa. Let's look at an example. In this particular thermochemical equation, we know that this is a reversible reaction because double arrows are used. Based on the enthalpy change, we know that this is going to be exothermic because it's a negative value. Hence, we can say that in the forwards direction, the reaction is exothermic and releases 58 kilojoules per mole. In the reverse or backwards direction, N2O4 can be converted back into NO2, and this reaction will be opposite in nature compared to the forwards direction. Hence, it will be endothermic and absorb 58 kilojoules per mole. Notice that the change in enthalpy is the same, but the signs are different for the forwards and backwards reaction. Occasionally, you'll often be asked to either draw or interpret the activation energy or the change in enthalpy for the forwards and reverse reaction. Questions will typically give you the energy profile for the forwards reaction, and from that, you should be able to work out what is the enthalpy change and activation energy for the reverse reaction. In this example, we know that the forwards reaction is endothermic in nature and has a delta H value equal to positive 40 kilojoules per mole. The activation energy for the forwards reaction can be found by subtracting 70 with 10, giving us an answer of positive 60 kilojoules per mole. To illustrate the energy changes for the reverse reaction, you want to first draw a mirror image that is superimposed on the original energy diagram. This means that you want to draw a mirror image that overlaps over the existing diagram. Some people can readily visualize the mirror image. However, if you cannot readily visualize it, you should be able to recognize that C and D are now the reactants for the reverse reaction and has an enthalpy of 50 kilojoules per mole, whereas the products A and B has an enthalpy of 10 kilojoules per mole based on the original diagram. From there, we can simply draw a hill, and this will give us the correct energy profile for the reverse reaction. For now, I'm going to erase the diagram of the forwards reaction to make it easier to interpret. The enthalpy change for the reverse reaction can be found by subtracting 10 with 50, giving us an answer of negative 40 kilojoules per mole. The activation energy for the reverse reaction can be found by going 70 minus 50, which will equal positive 20 kilojoules per mole. And using this example, you can readily see that the value for the change in enthalpy is the same, but the sign is flipped for the forward and reverse reaction. However, the activation energy for the forward and reverse reaction will always be different, but they both take on positive values. I would now like you to have a go answering a few questions. In this question, select the appropriate statement in regards to the forwards and backwards reaction. In this question, we should be able to recognize that A is going to be the activation energy for the forwards reaction, whereas B is going to be the activation energy for the reverse reaction. Hence, D is going to be the correct answer. Have a go with the next question. Please give yourself a minute to answer the following questions. For the first part of this question, it wants you to find the enthalpy change for the forward reaction. As a result, we're going to go 50 minus 150, giving us an answer of negative 100 kilojoules per mole. The second part wants us to find the activation energy, and this can be found by going 200 minus 150, giving us an answer of positive 50 kilojoules per mole. To answer questions 3 and 4, I'm going to need to draw the energy profile for the reverse reaction, which will look like this. To find the enthalpy change, I'm going to go 150 minus 50, which will give us an answer of positive 100 kilojoules per mole, and the activation energy can be found by going 200 minus 50 kilojoules, giving us an answer of positive 150 kilojoules per mole. In the last section of this video, I'm going to talk about multi-step reactions. We don't really cover multi-step reactions in the current VCA curriculum. However, you may sometimes see the energy profile diagram for them, so it's important for us to learn how to interpret them. A multi-step reaction is a reaction that proceeds in multiple steps, which ultimately results in the formation of the products. If you refer to the example on the right hand side, we know that this particular chemical reaction is a two-step reaction because there are two activation energies, or there are two hills. Beforehand, we only looked at energy profiles that occurred in one single step. As a result, you only saw one hill. Let's have a closer look to see what's actually happening in this two-step reaction. Firstly, NO reacts together by itself to form N2O2. To go from here to here, we know that this is going to be an exothermic process because the energy of the products is lower than the energy of the reactants. From there, N2O2 reacts with hydrogen gas to form N2O and water molecules. If we just examine this section of the energy profile, we know that this is going to be an exothermic process as well because the energy of the products is lower than the energy of the reactants. If we were to find out the overall energy change for this reaction, we should be able to tell that this is also going to be an example of an exothermic reaction. If you're ever dealing with a multi-step reaction, you're only expected to identify and compare the activation energies and the overall change in enthalpy. Let's have a look at another example together. In this reaction, A plus B forms C, and the overall equation is going to be an exothermic process. However, this process occurs in two steps, where A and B first react to form X, and from there it later then forms C. Which of the following best describes the energy changes during the course of the reaction? We know that in the first step, this is going to be an endothermic process. As a result, we can eliminate options A and C because the energy profile for an endothermic reaction should take on this general shape. When X forms C, this is an example of an exothermic process. As a result, it should have this general shape for the energy profile. Therefore, we can eliminate option B because the energy of C should be lower than the energy of X. Hence, D is going to be the correct answer. By now, you should be able to meet the success criteria in this video. This is the end of the video. Thank you for watching, and I'll see you guys again in the next one. Bye.